Hello and welcome to Algebra 1, Lesson 52. In this video, we're going to have an introduction to roots. So I know for some of you, you've learned about square roots in a previous course, but for others, you've had no exposure to it whatsoever. So we're going to just begin by talking about square roots. I'm going to pretend like you have no prior knowledge of it, and we're going to start from scratch. All right, so I want you to think back to when we first started talking about exponents, and we learned what it meant to square a number. So squaring a number means to multiply a number by itself. Basically, it's when you have an exponent of 2. So for these 4 examples here, we have 3 squared. So we know at this point that this is what? It's 3 times 3, or 9. If I have 4 squared, this is 4 times 4, or 16. If I have negative 7 squared with the negative and the 7 inside of parentheses, this is negative 7 times negative 7, which is positive 49. And then if I have negative 12 squared, again with the negative and the 12 inside of parentheses, this is negative 12 times negative 12, which is positive 144. Now, what if I gave you the following scenario? I have here that a squared, so something squared, is equal to 225. What is the value for a? So you might be thinking, how would I go about doing that? Well, let's just go back to a simple example. We saw that 3 squared was equal to 9, right? Why is it equal to 9? Well, I can further break this down and say it's 3 times 3, which equals 9. Now, if I think about a number that when multiplied by itself, so in other words, this would translate to a squared is equal to a times a, which equals 225. So I've got to think about a number that when multiplied by itself is going to give me 225. Can you think of a number? Well, if you can't, you can just break 225 down using a factor tree. So it ends in 5, so that means it's divisible by 5. 225 divided by 5 is 45. So let's write 45 times 5, and then 5 is going to be prime, so let's circle that. And then 45 can be further broken down into 9 times 5. 5 is prime, so let's circle that. And then 9 is 3 times 3, so 3 times 3. And those are each prime, so let's circle those. And what can I see here? I have 3 times 5, or 15, and then I have 3 times 5 again, or 15. So 225 is 15 times 15. So we've found a number that when multiplied by itself is going to give us 225. So where we have a question mark here, let me erase all this, I can put a value of 15. Now some of you will be screaming at this point going, well, what about negative 15? If I took negative 15 and I multiplied it by negative 15, I would also get 225. So you'd be correct there. So a could be 15, or it could also be negative 15, right? If I had negative 15 and that was squared, this would be negative 15 times negative 15, which would also give me a positive 225. So when we think about square roots, okay, we're going to think about a positive version and a negative version, and I'm going to show you the notation for that in a minute. All right, let's take a look at another one. So we have b squared equals 100. So we want to know what is the value for b. So if I took b squared and I said it's equal to what? Let's break this down into b times b. Let's say that's equal to 100. So all I'm looking for here is I'm looking for a number that when multiplied by itself gives me 100. So again, that's easy. Just make a factor tree for 100. And most of us know that 100 is what? It's 10 times 10. Right? I don't need to go through and go all the way to 5 times 2 and then 5 times 2 because I know that 10 times 10 is what I'm looking for, right? So b here would be 10, but again, it could also be negative 10, right? Negative 10 times negative 10 would also give me a positive 100. All right, so let's think a little bit about the notation involved with what is known as a square root. So in the previous 2 examples, we said a squared is equal to 225. And then we said, okay, a is equal to 15 or negative 15, right? Because 15 squared would give me 225. Then also negative 15 squared would give me 225 as well. And then we looked at a squared is equal to 100. And we said in that case, a was equal to 10, or it could be negative 10. Okay, so we want to think about kind of how this is asked to us in terms of our homework or a test, just moving forward. If I want what's known as the square root of a number, I'm going to see this symbol right here. So it looks kind of like this. So if I wanted to know what number squared would give me 225, I would put 225 underneath this symbol. And I would say this is the square root of 225, or what number, when multiplied by itself, gives me 225. We know at this point that the answer is 15. Okay, we found that here. Now, there's also a different way to kind of notate when I want negative 15. This right here is known as the principal square root, or the positive square root, so it produces a positive here. And then we have what's known as the negative square root. So if I want this one, I put a negative out in front. So I put a negative, and then everything else is the same. It's just asking me for the negative of this 15, which would be negative 15. Okay. Same thing would go for this example here. So if I want the square root of 100, this is the positive or principal square root of 100. So that's positive 10. And then the negative square root of 100, put a negative sign out in front, would be negative 10. Okay, so those are two different ways to kind of notate that. So let's look at kind of a general statement for this. If a is greater than 0, so we know that's a positive value, then we can say that the square root of a is a positive number that when squared gives us a. So in other words, if I have the square root of, again, I go back to 225. So this represents a here. So this is a positive number that when squared, when multiplied by itself, gives us this number back. So in this case, this is 15. Because 15 times 15 would give me 225, or that number that's inside of that symbol, back. Now, we have that negative outside in front of the symbol here. Negative square root of a is a negative number that when squared gives us a. So this is a, the number inside of here. So if I did negative square root of 225, the answer here would be negative 15. So you want to know the two different ways to notate that, because kind of moving forward on your test, if your teacher says, okay, I want the square root of, let's say, the number 9, you have to know that the answer is 3, just positive 3. If she was to say, I want the negative square root of 9, you have to know that the answer is going to be negative 3. And then kind of moving forward, as we get higher in math, you might see them put plus or minus the square root of 9. And then in this case, the answer is 3, or it could also be negative 3, right? Because I've accounted for the positive or principal square root of 9, and then also the negative square root of 9. So in that case, you get 3 or negative 3. All right, let's just go through some examples real quick. If I have the square root of 0, okay, the square root of 0. 0 is not a positive or a negative number. It's just 0. So in this particular case, what's it going to be equal to? What number multiplied by itself gives me 0? Well, 0 does. So this is an automatic. You see this on your test, you have the square root of 0. It's just equal to 0. Now the next one, we have the square root of 4. And then after that, we have the negative square root of 4. So the positive or principal square root of 4 is what? It's 2, right? Because 2 squared is going to give me 4, right? What number multiplied by itself gives me this? Well, it's 2, right? 2 squared is 4. Then for this one, I have the negative square root of 4. So what negative value, when multiplied by itself, is going to give me 4? Well, that's negative 2. So you can see the difference in the notation. Principal or positive square root of 4, negative square root of 4. So something you really need to pay attention to. All right, what about the square root of 16? Can you think about a number that when multiplied by itself gives you 16? Again, if you don't know that off the top of your head, always just build a factor tree. So I could say, okay, 16 is what? A lot of you right away know it's 4 times 4, but let's say you didn't. Let's say you start out with 8 times 2. You know that 2 is prime, And for 8, you know that's 4 times 2. And you know 2 is prime. At that point, you could stop because you say, okay, 2 times 2 is 4. You'd have 4 times 4. But let's say you just kept going. Okay, we keep going. This is 2 times 2. So now you see that you have what? 2 times 2 or 4. This is 4 times 2 times 2 or 4. Right? So 4 times 4, which is 16. So a number that is multiplied by itself that gives me this is my answer. Right? So the square root of 16 is 4. And then what about the negative square root of 16? Well, again, what negative number, when multiplied by itself, is going to give me 16? Well, negative 4, right? Negative 4 times negative 4 is positive 16. All right, what about the square root of 400? Well, a lot of you are not going to know what number multiplied by itself gives you 400. So let's just start out with a factor tree. So 400, I know it ends in 0, so it's divisible by 10. So this would be what? 40 times 10. And 10 I can break down into 5 times 2. Those are each going to be prime, so let's circle those. Then for 40, I can break that down into 10 times 4. And 10 is 5 times 2. And 4 is 2 times 2. So let's circle all these. So what do I see here? I've got 2 5s. So 5 times 5. And I've got 4 2s. So times 2 times 2 times 2 times 2. Well, what I can do is I can write this as what? 5 times 2 times 2 times 5 times 2 times 2, or 5 times 4, which is 20, times 20. 20 times 20 is 400, so that's your answer. And sometimes when you don't know these off the top of your head, you've got to do a little bit of work, but pretty much in Algebra 1, they're going to keep giving you kind of the same ones over and over again, so you'll memorize them very, very quickly. You also have something on your calculator, if you're allowed to use it, known as a square root key, right? So you type in a number and then hit square root, and then it's going to give that to you automatically. So the square root of 400 would be 20. Now, again, we have the negative square root of 400, and so this is what? This is negative 20. Since negative 20 times negative 20 would give you 400. All right, so we're also going to see this with fractions as well. So we have the square root of 9/16. So just think about what fraction times itself would give me 9/16. Well, just break up the numerator and denominator kind of separately in your head. What number multiplied by itself would give me 9? We know that would be 3. Then what number multiplied by itself would give me 16? We know that would be 4. And you can check it. Would 3/4 times 3/4 give me 9/16? 3 times 3 is 9. 4 times 4 is 16. So yeah, that does check out. All right, so let's talk about something that is going to come up kind of as we move forward. When we square the square root symbol, the two cancel each other out. So squaring and square root are opposite operations, just like multiplication and division. So in other words, if I had something like 5, I start with that. Let's say I divide 5 by 3, and then I multiply by 3. Well, what's going to happen? I'm going to end up with 5 again, right? Because this operation, the division, cancels with the multiplication, right? If I divide by 3, but then I multiply by 3, I just start out with that original number 5, right? So this just equals 5. It's going to be the same thing. If I started out with, let's say, 5, and let's say I have 5, and I square 5, but then I take the square root, I'm going to end up with 5 again, right? 5 squared is what? It's 5 times 5, that's 25. And then if I took 25, and I took the square root of it, I'm going to end up with 5 again, right? So it's just like multiplication and division, they're opposite operations. So we have here the square root of 15 that's squared. So in other words, I start out with 15, I take the square root of it, but then I square it. So it's like I can cancel this, and I'm just left with this, right? And another way to show that is just to say, okay, well, what I have here is I have the square root of 15 times the square root of 15. So whatever number it is, okay, for 15, that multiplied by itself gives me 15, it's multiplied by that number, so I would just get 15. right? As an easier example, let's say I had something like the square root of 4 squared. So writing this the same way, this is square root of 4 times square root of 4. Does this equal 4? We know that the square root of 4 is 2. So what is 2 times 2? Well, 2 times 2 is 4, right? So that's where this comes from. Kind of the shortcut to this is just to say, okay, well, this is going to cancel with this, and I just have this. So what if I had the negative square root of 31 squared? So if I square a negative, right, you think about that as just negative 1. Negative 1 times negative 1 is 1. So this and the square root are going to cancel, and I'm going to be left with 31. Again, if you want to think about this in a different way, think about if you had negative square root of 31 multiplied by negative square root of 31. Negative times negative is positive, of course. Square root of 31 times the square root of 31 is just 31. All right, so this one's a bit more complex, but we follow the same logic. So we have the square root of 8x minus 7, and this is squared. So this is going to cancel with this, and I'll just have what's inside, which is 8x minus 7. All right, let's talk a little bit more about rational numbers and irrational numbers, which we've kind of covered before, but I want to make sure that you have kind of a strong foundation in this before we get to Algebra 2 and we really start knocking some numbers around. So I want you to recall that a rational number, let me just highlight that, a rational number is one that can be formed from the quotient of two integers. In decimal form, it's going to terminate, okay, or it's going to repeat the same pattern forever. So you've seen examples where you get something like 21.3, and we put a bar over the 3 because the 3 repeats forever. That is a rational number. Or you've seen something like, let's say you have 0.687, 687, 687, where the 6, the 8, and the 7 repeat forever, right? And we could erase this and just put a bar over this. So that pattern repeats forever. Or it terminates. So you might just get 0.682591, and it stops. Those are rational numbers, right? You can always form these from the quotient of two integers. So I should be able to say this is, let's say, 28 over 3. One integer over another. So any number whose square root is a rational number is called a perfect square. A perfect square. You're going to hear me talk about that all the time. You've also heard me talk about this when we were talking about polynomials. I refer to a perfect square trinomial. So to go back to an example that we already know, the square root of 225 is what? It's 15. 15 is a rational number, so therefore 225 is a perfect square. And then as another example that we already know, the square root of 9 is what? It's 3. So 3 is a rational number, so therefore 9 is a perfect square. What about the square root of 1/4? Well, this is what? Square root of 1, if I think about what times what would give me 1, it's 1. What times what would give me 4, it's 2. So the square root of 1/4 is 1/2, and so therefore 1/4 is a perfect square. All right, now let's talk a little bit about irrational numbers. So an irrational number is one that cannot be written as the ratio of two integers. So I can't say, okay, this is 15 over 4, for example. I can't do that with an irrational number. There are no two integers that I can put over each other to give me that irrational number. So its decimal does not terminate, okay? It does not terminate, nor does it repeat, okay? So something like the square root of 2. You cannot find two integers that you can put over each other that would give you the square root of 2. If you type this into a calculator, you're not going to get an exact value. Your calculator's either going to round or it's going to truncate, and it's going to give you an estimate for it, but not an exact value. And usually, we'll say this is approximately equal to 1.41. But if you type it up on a calculator, and I just typed it up on mine, I get 1.414213562. So after that final digit that you get, realize that it continues forever and ever and ever, and it's not going to terminate or repeat the same pattern. So that's the problem with an irrational number. You you can't really work with it that easily. A famous example of this is pi. And we talked about this before when we talked about direct variation. And I gave you an example where in the Hollywood movie, The Life of Pi, this guy, when he was a child, is on a blackboard and he's reciting all these digits of pi, right? And you can go on a computer and go into Google and you can find websites that give you all these digits of pi. No matter how many you list, it just keeps going forever and ever. You can't list all of them. So that's the problem, again, with an irrational number. So when we get an irrational square root, generally we will approximate by rounding to the nearest hundredth. And sometimes you won't approximate at all. Sometimes you're just going to leave it like this. But in some cases, it's necessary to kind of do an estimate. In other cases, you can kind of leave it like that. It just depends on the scenario you're dealing with. So square root of 11, for example, would be approximately, punch that up on a calculator to get about 3.31, 66247. And let me kind of stop there. If I round it to the nearest hundredths, that would be 3.32. So 3.32. What about square root of 7? So you punch that up on a calculator. If we round out to the nearest hundredths, you'd have something like 2.65. All right, so now that we understand kind of the basics of finding the square root of a number, and we know the difference in notation between finding the principal or positive square root and kind of the negative square root, we've got to move into some kind of harder material. So the first thing that students struggle with would be the square root of a negative number, okay? So we also need to understand that not every real number has a square root. So if I ask you for the square root of -4, what am I asking you for? The first thing students might do is they might get confused and say, well, I'm thinking back through this lesson that we just had, and he already covered this. This is negative square root of 4, and this equals -2. No, that's not what I'm talking about. In this case, the number under the square root symbol is a 4. Okay, it is a positive value. The negative is outside. This is outside. Okay, that's a big deal. Now, in this particular case, I have the -4 inside this little symbol. So what I'm saying is, what number, when multiplied by itself, is going to give me -4? The answer to that is it does not exist. Okay. Now, when we get higher in math, we're thinking about these imaginary numbers, but in our real number system, does not exist, right? You can't square a number and get a negative number, right? You can't do that because a negative times another negative is going to give you a positive 100% of the time. So there's no number that if I multiply by itself is going to give me a -4. So we would just put not a real number. Okay, it doesn't exist. And you can try that on your calculator. And depending on the calculator, you might get no real answer. You might get not a real number. You might just get error, so on and so forth. Because the computer cannot calculate a number that when multiplied by itself is going to give you a -4. All right, so now let's move on and talk about some higher level roots. So we saw that the square root is the reverse of squaring. So similarly, the cube root is the reverse of cubing. So cubing is nothing more than just raising something to the third power. So in other words, if I had 2 cubed, this is what? This is 2 times 2 times 2, or just the number 8. So if I reverse that process and I said, here's my 8 here, the symbol looks the same. All I'm going to do is, instead of having nothing here, I'm going to put a 3. That tells me I want the cube root of 8, or I want a number that when multiplied by itself 3 times, okay, 3 times, is going to give me 8, and we know the answer to that is 2. All right, so in general, when we work with roots, okay, not just square roots, but roots in general, you kind of think about, okay, A, the number that is underneath the symbol is known as the radicand. So this is the radicand. This is something that they might test you on when you first get the square root. So this is the radicand. N is known as the index. Okay, this is the index. And the index is important because it tells me what I'm looking for. So for example, when I just saw the cube root of 8, my index is 3, right? My radicand is 8. So I'm saying what number, again, when multiplied by itself 3 times, would give me 8. If I had something like, let's say the 4th root of 16, okay, I'm doing easy stuff. The fourth root of 16 is asking what number, when multiplied by itself 4 times, is going to give me 16? Well, we would think about 2. You could also have negative 2, right? But it would be a different notation. But 2 times 2 is 4, times 2 again is 8, times 2 one more time is 16. And again, you could also say the fourth root of 16 would be negative 2. But again, there's that different notation for that. Now, this symbol here is known as just a radical symbol. A radical symbol. And then the whole thing, okay, so the whole thing is known as a radical. So if your teacher comes in and says, we're studying radicals today, or we're studying roots today, okay, they're basically talking about the same thing. Now, one thing you would have noticed already is that when we have the square root, we don't write the 2, right? The index would be a 2, but we don't write it. It's left blank. So that's one property of square roots. If you write a 2 up there, it's not incorrect. It's just not traditional. So if I put, the square root of, let's say, 16 like that, it's the same thing as if I put the square root of 16 like that, right? In each case, it's 4. This is just a notational thing that we do. So this one right here, if I have an index of 3, this is the cube root. If I have an index of 4, it's the fourth root. If I have an index of 5, it's the fifth root, right? So on and so forth. You can put any number you want there, but it starts getting very, very complex. If I'm looking for the fifth root of something, I'm looking for a number that when multiplied by itself 5 times gives me that number, the radicand. So again, let's look at some easy examples of this. If I have the cube root of 8, again, what number when multiplied by itself 3 times gives me 8? We know at this point that that's 2, right? 2 times 2 is 4. 4 times 2 is 8. So now we have the fourth root of 16, which we already looked at. Again, what number, when multiplied by itself 4 times, gives me 16? Well, that's going to be 2. And this is the principal fourth root of 16, so I want a positive 2. If I want a negative 2, then I would look at the negative fourth root of 16. In this case, this is negative 2. This one is one you have to pay attention to. We know that in the case of a square root, so let's say I want the square root of negative 16. I already talked about the fact that that's not a real number, right? I can't square a number and get a negative result. Negative times negative is positive. If I'm asking for an even root, so something to the second power, let's say to the fourth power, so on and so forth, this is not going to be a real number, right? It's not going to be possible, right? Because an even number of negative signs, when multiplied together, gives you a positive. If I have an odd index, like I have here, it is possible, right? Because an odd number of negative signs would, in fact, give me a negative result. So if I had something like the cube root of negative 8, this is a real number. It's negative 2. Negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. In this case, we have 5. 5 is an odd number. So I can have the fifth root of negative 32. That would just be negative 2. To show you that, just think about negative 2 times negative 2 times negative 2 times negative 2 times negative 2. You have 1, 2, 3, 4, 5 negatives. So that's going to be a negative. And then 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So that is negative 32. And so again, the fifth root of negative 32 would be negative 2. So again, a radicand with an odd index, 3, 5, 7, 9, 11, so on and so forth, can have a negative radicand. So this part right here can be negative, again, if you have an odd index. If you have an even index, it cannot be. And the reason for that, again, is you won't have a real number that will satisfy that. So if I look at the cube root of negative 27, what number, when multiplied by itself 3 times, would give me negative 27? Well, it would be negative 3. Negative 3 times negative 3 is positive 9. Positive 9 times negative 3 is negative 27. So let's look at the fifth root of negative 1024. So again, if I have an odd index, this can be negative. And when I'm solving a problem like this, I would just automatically write a negative there, right? If I had 5 negatives, I would get a negative. So I can just think about the number part. So 1024, kind of break this down with a factor tree. I know it's divisible by 4 because 24 is. If I divide 1024 by 4, I'd get 256. So 256 times 4. And 4 I know is 2 times 2. And let me circle those. So what about 256? Well, I know that's divisible by 4. This is 4 times 64. And 64 is divisible by 4. This is 4 times 16. And 16 is divisible by 4. This is 4 times 4. So without continuing on this factor tree, I've got 1, 2, 3, 4, and this original one up here, 5 factors of 4. So if I multiplied 4 times itself 5 times, I would get 1024, and that's what we're looking for. So this would be negative 4 as your answer. So let me erase this real quick, and I can show that to you real quick. So you'd have negative 4. This quantity would be raised to the 5th power, and this would be equal to negative 4 times negative 4 times negative 4 times negative 4 times negative 4. 1, 2, 3, 4, 5 negatives gives me a negative. 4 times 4 is 16. 16 times 4 is 64. 64 times 4 is 256. And if I multiply 256 times 4, I get 1024. Right? Stick that next to the negative, and I get my negative 1024 back, which was my radicand. So then what about the 6th root of negative 729? Do we need to look to solve this? No, because I have a negative here, and I have an even index, so this is not a real number.